This is Saranya Chejalla. Welcome to ECP Tech. In this class, we are going to learn about one of the major important design issue of data link layer is nothing but error correction and error detection technique. So, firstly, we talk about an error correction technique in this video. Let us get into the topic. Error correction. Before going to the error correction, we have to know what is meant by error. The error is a situation when the sender's data does not match with the receiver's data. When the sender's data does not match with the receiver's data. See, there are many reasons we have that error will occur in our data. It may be a noise, or it may be a crosstalk, or it may be any frames corrupted, or unnecessary data will enter into our original data. So these are the lot of reasons we have that error will occur in our original data. See, for this reason, the data link layer uses some error control mechanism to ensure that frames and transmit in one level of accuracy to transmit a certain level of accuracy. That means the data will be sent at a given time period, and we have to send a reliable data to control all the errors from source to destination while transmitting the data from source to destination, right? See, we have a different type of errors here. Single bit error, multiple bit error, and burst error. These are the types of errors we have. So, let us talk about what is meant by a single bit error and what is meant by a multiple bit error and what is meant by a burst error. See this diagram. So, this is a single bit error. Single bit error means this is an actual data, right? So this is on sender side and this is on receiver side. Sender side and receiver side. So here one bit is changed. In place of 0, we get an 1. So only one bit is changed. That will be considered as a single bit error. Okay. Multiple bits errors. Multiple bits errors. Let us see the sender side of data and receiver side of data. So in third position we have 0. In sender side it is a 1. In fifth position we have 1. From the sender side it is a 0, I think. Okay. So it is changed. See, compare the sender side data and the receiver side data. So two or more bits are changed here. So we can consider this is a multiple bit errors. Burst error. Burst error means the complete data will be changed. The complete data will be changed. See, observe the sender side data and the receiver side data. So the data is completely changed. The data is completely changed. See this? The data is completely changed. So these are the three types of errors may occur in our data while transmitting the data from source to destination. So this to reduce or to eliminate these type of errors, the error control mechanism introduces two type of techniques, or two ways we can call it as two ways. See, these are the two possible ways: error detection and error correction. Now we are talking about an error correction. It is the one type of error control mechanism. It is one type of error control mechanism. So error correction codes. What is the purpose of error correction codes? The error correction codes are used to detect and correct the errors. To detect and correct the errors when data is transmitted from sender to receiver. Data is transmitted from sender to receivers. In this also, the error correction control mechanism handled two possible ways. Handled two possible ways. We have a two types of corrections: backward error correction and forward error correction. Backward error correction and forward error correction. See, each and every error correction we have some functionality. See, backward error correction means once the error is discovered, the receiver requests the sender to retransmit the original data. To retransmit the original data means whenever the receiver identifies there is an error in the data unit, it gives an one acknowledgement to the sender. Please send the original data unit again. The original data unit again. There is an error in the data unit. There is an error in the data unit. This is an one type of error correction. We can call it as backward error correction. Next, forward error correction. Forward error correction means the receiver uses some error correcting code. The receiver uses some error correcting code to automatically correct the errors. To automatically correct the errors. See, mainly the error correction uses this forward error correction technique. In this, we have one small thing. If you want to correct the errors in a data unit, you have to know the exact position of the error. You have to know the exact position of the error. Then only we can identify that particular position. Then only we can correct that error into actual data or original data. Right? See, in this forward error correction technique or error correction technique, we have to change only a single bit. We can change only a single bit. So single bit errors only modified by using this forward error correction technique. Single bit errors only modified by using this forward error correction technique. See, the most efficient error correction technique we use this type of errors is Hamming code. Hamming code. The Hamming code is one of the very efficient error correction technique to solve the single bit error. To solve the single bit error. Right. See, what is the purpose of Hamming code? What is the functionality of the Hamming code? How can we identify the exact position of the error in the data unit? How can we correct the error in the data unit, right? So let us see what is meant by Hamming code. Hamming code is a set of error correction codes. We already know that. So it is used to detect and correct the errors. So here the Hamming code mainly generate what type of technology to identify the position of the errors. To identify the position of error means to identify where the error is occurred in the data unit. See, this was introduced by an or developed by R.W. Hamming. R.W. Hamming. So, the name come for this error correction technique is Hamming code. See, here in this Hamming code, we use an redundant bits to identify the error. We use an redundant bits to identify the errors. What is meant by redundant bits? The redundant bits are extra binary bits that are generated and added to the information carrying bits of data. Means it will be added to the original data. Original data. These redundant bits or the binary bits means ones and zeros that are generated and added to the original data. So, what is the use of these redundant bits means when calculate these redundant bits, we have to get all the zeros. We have to get all the zeros. Otherwise, we get any other numbering here means instead of all zeros, we get any one. We can say that there is an error in the data unit. That there is an error in the data unit. So, it is used for um to correct the errors. Here we see the formula how to calculate a redundant bits. How to calculate a redundant bits. So 2 power of r greater than equal to m plus r plus 1. M plus r plus 1. So here where r is a redundant bit and m is an original bit or a data bit. Original data bit or a data bit. Okay, right. Let us see one of the example. How can I identify the error? how can this is an actual data, how can I identify this is an actual data, this is an error data? I will show the example here. I solve this example. Let us look into that. So this is an example. See, for example, I take the data of 7 bits. 7 bits. So what is the data? This is an actual data. 10 double 10 double 1, and this is an actual data bits. Okay. Let us assume redundant bits. Redundant bits means we have to assume how many redundant bits we added. Identify the redundant bits first in the data bits. Identify the how many redundant bits are added to the original data, we have to identify, right? See, I'm here. Let us assume the redundant bits is 3. Okay, so I'm calculating in this formula. I already said 2 power of r greater than equal to m plus r plus 1. M is equal to actual data bits, r is equal to redundant bits. See, here I assume the redundant bits is 3, right? So 2 power of 3 greater than equal to 7 plus 3 plus 1. 7 plus 3 plus 1. 2 cube. We know that 2 cube is 8. It is greater or equal to 11. So, wrong. So, in this case, this is failed. Means we are not adding 3 redundant bits. We are not adding 3 redundant bits. See here, we have, you get another doubt why the redundant bits is not from an 2 or 1. You can raise the doubt, but while I am taking the redundant bits is 3 only, I get a low value here. I get a low value. So from that I am taking, and from 3 onwards I assume that redundant bits. From that I solve this a particular formula or example. See, assume redundant bits is 4. So this is lower, and assume redundant bits is 4. 2 power of 4 greater than equal to 7 plus 4 plus 1. So 2 power of 4 is 16 and 12. See, this is an right. Okay, so it satisfies the formula. Means how many redundant bits we added this particular data means, how many redundant bits we added this particular data means 4. 4 redundant bits we added. So in which positions, we add this redundant bits? So the data frame size is, so 7 bits is an actual data, 4 bits are redundant bits, total 11 bits are the actual, means the size of the data frame. The size of the data frame. Why I call this is an data frame is the data link, in data link layer the data is in the form of frames, so I call it as data frame. Okay. See, we identify that 4 redundant bits or we use in a particular data bit. See, in which positions we inserted that bits, in which position we inserted that bits in data unit, we have to identify. See, 4 redundant bits. Okay, so from 0 onwards I'm telling 2 power of 0 p1, 2 power of 1 p2, 2 square p4, 2 cube p8. So in this, these are the redundant bits, we can also call as an parity bits. Redundant bits is also called as an parity bits. So one or more parity, we can call as one or more parity bits, but in a different positions we are inserting means, in the middle of the data frame we are inserting means, we can call it as redundant bits. So this is an actual data. See, this is an actual data, right? So 7 plus 4 is equal to 11 bits. I wrote an 11. Okay. P1, P2, P4, P8. So in these 4 positions, I inserted the redundant bits, right? So remaining are an data units, data bits. Data bits. Remaining are the data bits. This is the entire data frame, right? So here we have to insert, means we don't know in that particular positions we use ones or zeros. we uh, we entered ones or zeros, we don't know. We identify the positions where the redundant bits, redundant bits I already said, this is one of the binary bits we inserted into the data, right? See, what type of bits means, it means ones or zeros we insert in a particular position, we have to know that. So 11 bits means we have a binary calculation for 11 bits. So see, this each and every bit in binary format I wrote 6, 7, 8, 9, 10, 11. Okay, these are the binary format. So I have to identify the P1. So in this uh, we use 1 or 0. I already said these redundant bits or the parity bits. Parity bits for parity checking. So consider this data unit as an even parity. Consider this data is an even parity. We have to know the even parity. So first of all, to identify the parity bits means parity bits means P1, P2, P4, P8. These are the redundant bits we called as. Okay, we have to identify the each and once P1 in this data unit where the ones we have inserted. So identify the first position ones. So 1, 3, 5, 7, 9, 11. So these numbers has a first position ones. P1. P1 means the first position ones. Okay, right? Next P2. P2 means the second position. The second position ones we have to write. So 2, 3, 6, 7, 10, 11. This is the second positions ones. Next P4. P4 means the fourth position ones. Fourth positions ones. See, 2 power of 4, 4, 5, 6, 7. So fourth position ones means in this binary format 1, 2, 4, 8, 16, 32, 64. This format we can consider in the binary format. That's why fourth position ones means here 1, 4, 5, 6, 7. I wrote fourth position ones, and the eighth position ones. P8 means eighth position ones. 8, 9, 10, 11. Okay. So now calculate. So I consider this is an even parity. Even parity means we get for even number of ones we consider 0. For odd number of ones we have to insert 1. Okay. So make this as an even parity. Make this as an even parity. Even parity means we have to include that particular bits, or we have to get an zeros. Even parity means all the redundant bits we get an zeros. Okay. So here 5 ones, 5 ones. So to get an even parity, I put an 1 for P1. I put an 1 for P1. So even parity. Next, here also we got an odd number of ones, 3 ones. To get an even parity, I put 1 for P2 position. I put 1 for an P2 position. Next, here 1, 1 is a even number of ones. So to get an even parity, I put P4 is 0. Next, here also you got an even number of ones. So for to get an even parity, I put P8 is 0. So what is the actual data? The data will come like this. See, 1, 0. So 1, 0, 1. So eighth position I put 0. So this is an 1 parity bit. Next, this is an another parity. This is an another parity, and this is an another parity. So 1, 1, 0, 0 we inserted. So this is an actual data bit. Okay. So sender side actual data bit. This is a sender side. And this is a receiver side. So if the exact data will be get to the receiver side, so we'll get an all zeros. We'll get an all zeros. Okay, while there is an error occurred in the middle of the bit. We already discussed that the error correction technique for single bit error we are using this type of Hamming code. So I'm modifying one bit here. I'm modifying one bit here to identify the error. So in the sixth position, I'm putting instead of 0, I'm putting 1 instead of 0. Okay, so this is a single bit error. How can the receiver identify the position of the errors? How can it rectify that? Okay, so identify the error. Again, do the same thing where the sender said we do the what are the process we did. So in the receiver side also same process we have to do. See the P1 I put 1, 3, 5, 7, 9, 11. Okay, 1, 3, 5, 7, 9, 11. So all ones 0. Okay, so in this particular format, in this particular bits, there is no chance of errors in this particular position. So 1, 3, 5, 7, 9, 11. P1 is 0 means even parity. We get an even parity, so there is no error in these particular positions, right? Next, P2. 2, 3, 6, 7, 10, 11. So we'll get an odd number of ones. So this is an odd parity. So in this we have a sixth position. I modified C instead of 0. I modified 1. Okay, right? So P2 I get an 1. P4. Again in this also we have a 6. Thus we get an odd parity. So P8 position 8, 9, 10, 11. We don't have any error. That is 0. So see, after adding these all, we get an 0, double 1, 0. 0, double 1, 0. That is an position of 6. So I changed the sixth position 1 instead of 0. Right? So this is the process to identify the error in the data frame. To identify the error in the data frame, we have to rectify that error. So by using this error coding techniques, the receiver identify the position of the error where that error occur in the data unit. Where that error occur in the data unit. If we get all the zeros, if we get all the zeros of redundant bits, so there is no error occur in the data frame, we can conclude that. Okay, the receiver will accept the data frame. If a single bit error means one bit is changed in the data frame, so that comes to the single bit error. So to identify the position of the error, the following process we have to done by a receiver. The same process what we done from in the sender, what we did in the sender, the same process will be do in the receiver side. We have to identify that the position of an error. So this is the process of Hamming code to identify the position of error in the data frame, and it is a very efficient technique to identify the single bit error. So it is not suitable for to identify the multiple bit errors or burst error. For single bit error we are using a Hamming code, right? So this is the example of an Hamming code. By using this Hamming code, we can identify any number of single bit errors. We can identify the position of the error where it will occur. Okay. So these are the one of the very efficient error correction technique we are using mostly. So this is about an error correction technique. In this video, we learn the one of the major design issue of an data link layer is error correction technique. We already discussed that what is meant by error, how the error will comes, what is the reasons the error will occur in our data frame. So I already said noise, crosstalk, whatever it may be. Okay, so we also see the example how to correct the errors, forward error correction. So this is the about and forward error correction to correcting the errors. We are using some error coding techniques to correct the errors. We have to identifying an position of the error where it occurred. Okay, right? So these are about an error correction techniques. So error detection techniques will be continue in the next class. Kindly like, share, subscribe. Easy BTech. Thank you.